Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Elisabeth Newton with us today. Hey, Elisabeth.
Hello, nice to be here.
Great. Where are you at these days?
So I am a professor at Dartmouth College. I live across the border in Vermont. So I'm currently calling in from my kitchen, which is the only place in the house that gets direct sunlight. So it's one of my favorite spots to work.
Well, awesome. I'm going to guess you have a nice view out your kitchen window of the Vermont countryside. So if you do want to, go ahead and turn your computer and let's take a look at your kitchen view window.
Yeah, so I do have quite a lovely view. I'm renting an in-law apartment. So we live next to our landlords, and they have this lovely property. So that's Mount Escutney, which is a state park off in the background.
Cool. And there's a barn.
And there's a barn. They have horses.
Horses. Do you have animals?
I have two cats. One has just been here trying to beg some food off of me. He knows that if I sit at the kitchen table, there could be food coming to his way.
Aren't there like mice out in the field they can go catch?
Oh, there's mice in the house they can catch and do, thankfully.
And then they bring them to you as gifts.
Yeah.
Great fun, great fun. So is Dartmouth still, they're still doing everything online?
Yes, so some of the undergrads are back, but most of the classes are still remote. I do have an on-campus section for my class where the students are going to get to participate in the telescope lab, where we actually have some small teaching telescopes that they get to check out and make some observations with. Very, very small teaching telescopes.
Yeah. It's not CAC. Definitely not. Cool. So I imagine you'll be back all in person for the fall. Is that the plan?
Yes, that is my expectation. I'm not actually teaching in the fall, so I will be back in winter.
Good for you. Are you on sabbatical or something?
So we actually we teach during summer as well. So our students are on campus the summer after their sophomore year. So I'm often teaching summer and not one of the other terms.
Fair deal. Fair deal. Very cool. Elisabeth, what do you like to do for research?
So I have two branches to my research. I study stellar astrophysics, so especially stellar rotation and magnetic activity, and particularly for M-dwarf stars, those trying to understand how these really small stars evolve with time. And then more recently, I've started research on young exoplanets, which the connection there to the stellar rotation and activity is that the stars are really important, especially when you're studying young planets.
Indeed. And that is going to take us to this really lovely AJ article. TESS hunt for young and maturing exoplanets. Time. Number 4. 3 small planets orbiting 120 mega-year-old star in the Pisces-Eridanus stream. And Elisabeth, take us away.
Yeah, so this is a paper born out of our collaboration THYME, which is, I would say, not bad for an astronomy acronym. So the TESS hunt for young and maturing exoplanets. So like it says, we're using data from NASA's TESS mission to try to find planets around young stars. So that we can then, the overall goal here is that we can find planets orbiting young stars so that we can understand the planet formation and evolution process. So we know from Kepler, from K2, from Corot, that we have a population of planets around older stars that have certain properties, masses, radii, orbital periods. And the question is, how did we get there? And there's a lot of ways to answer that question. The approach that we're taking is to try to find these planets that are in the process of evolving.
They've cleared their disks.
Yes, it does turn out that this star does seem to have an infrared excess that would be indicative of a debris disk, but a very faint and cool one, not anything particularly spectacular.
Okay, good. Okay.
So this particular story of this young planet starts with a stellar astrophysics story. And it starts with a paper by Meingast et al. That was using data from Gaia to try to identify new associations of stars. And so using this public data from Gaia, they found a new association, which was later called the Pisces-Eridanus stream. And so this is about 100 parsecs away, so it's not very far, but it's also 120 degrees across. So it spans a very large fraction of the sky, which is, I think, basically why people hadn't found it before data from Gaia was available.
Yeah.
Originally, this group of stars they thought was a bit older. They thought it was actually more like 1 billion years. That would have been a really interesting stellar astrophysics story in that case, because how do you get something that's still associated at 1 billion years old? However, it turned out that the whole association is actually much younger. So in another group led by Jason Curtis, used data from TESS that already existed to look at the rotation periods of stars in the cluster. And the rotation periods indicated a much younger age. And actually, if we skip ahead to figure 7, I can show you what the data on this cluster actually looks like.
Let's take a look at figure 7. All right, and I'm going to blow that up a bit. People to see.
Yeah. So excellent. So if I look at figure 7 here, this shows rotation period as a function of color. The black points are data of our stars in the Pisces-Eridanus stream from this paper by Jason Curtis that I already mentioned. And then the teal points are stars in the Pleiades, which is 120 million year old, very well-studied cluster. And so what Curtis and his collaborators found is that when they measured the rotation periods of stars in the Pisces-Eridanus stream, as you can see in this figure, they looked very similar to the stars in the Pleiades. And that is telling us that the Pisces-Eridanus stream is the same age as the Pleiades. And so that's how we determined that the age of this cluster is 120 million years old. So I actually was down visiting the Flatiron Institute in New York and Jason gave a short presentation on this discovery of the age of the system. And I immediately was like, oh, can I have your target list? Because I'd really like to cross-match it to the TESS objects of interest, the possible planet candidates that the TESS team at MIT was putting out. He sent it to me, cross-match them, and I was like, oh, look, TOI 451 is a TOI, so a candidate planet host that is also a member of this stream. And so in terms of the THYME survey, what the Pisces-Eridanus stream offered was a brand new opportunity to look for planets around young stars.
Very nice.
And so this red star here at a color of 1 and a period of about 5 days, that's TOI 451.
Okay. Very nice.
Awesome. Okay, so yeah, that's the story of how we even knew to try to look for this.
Very nice.
And
visit there to Flatiron.
Yeah, it was I just really liked the story of like, oh, there's this new cluster that public data let us identify, us generally in astronomy. Then other public data let us identify the age of the cluster, and then other public data then let us actually identify that there was a planet in there. So this kind of the story from the discovery of the stream to the discovery of the planet was enabled by these large surveys that have been made publicly available to the community. And I just actually, there's some discussion amongst our team about who is going to lead what paper. And I was like, I'd really like to lead this one because I'd like to tell that story of how we got from point A to point B. So here we are.
Very cool.
Cool.
Right, so what should we look at next?
What was that?
What should we look at next?
Let's scroll all the way back up to figure 1.
Figure 1. Non-linear is good. Okay, so now we got our object and we are going to do some test data.
Yeah. So this is our key plot for this paper, which is both the starting point for the survey and basically the ending point as well, or the starting point for the work and the ending point. So the top panel shows the flux versus time. That's the TESS data. So we have 2 TESS sectors, so 2 27-day spans of time back to back. And the main variability you can see in the gray points is the stellar variability. And that's modeled with a Gaussian process, which is the blue line.
Okay.
So you've already seen in the previous plot that the star has a period of around 5 days, and that is exactly what you're seeing this modulation as. So if you go in, you can probably pause the screen and measure that it's about a 5-day rotation period. This is the rotation period that it should have for a star in Pisces-Eridanus. It's got fairly high amplitudes of variability, which is typical of a young star as well. But then, of course, what's unique about this particular star in Pisces-Eridanus is that it also has transiting planets. So that's there's 3 planets in the system. Originally, actually the first TOI alert only had 1 planet. We quickly realized that that was actually a combination of TOI 451C and D. So we pretty quickly figured out that there were 2 planets in the system. So that's the 2 longer period, deeper transits. The plots on the bottom, the y-axis scale changes per planet. So, but the TOI 451D is the deepest, C is the middle. And then B is the smallest one. And TOI 451B, we actually didn't realize was there, even though probably we should have, until a couple different lines of evidence made us kind of go back to something, to the signal that we had previously, some combination of discarded and not known what to do with. So ultimately, we found a 3rd planet in the system, which is TOI 451b. It's the smallest of the 3, and it's the shortest period.
So did 451A get split into C and D, or is there just no 451A?
Yeah, so that's the uniquest exoplanet naming conventions. So technically speaking, like the star is TOI 451A kind of, so planet naming starts at B. So originally we had TOI, so the original TESS alerts are not given letters, they're actually just given numbers since they aren't validated or confirmed planets yet. So TOI 451.01 became TOI 451C and D. And yeah, and then there was a TOI 451.03 that became TOI 451B. So we renumbered them. So, you know, often traditionally exoplanets are, the BCD is not the order of the orbital period, but the order of discovery, right. Which I did take the liberty of dispensing with that, given that we were publishing them all in the same paper, and I renumbered them to go in order.
Discoverer's rights.
Yeah. Yeah, so on the top panel here, each of the vertical lines indicates the transits of one of the planets.
Yeah, blue there, pinky there, purpley there. Yep.
And then the bottom panels are the phase folded and binned transit light curves for each of them, along with some samples from the Monte Carlo fitting process that we did.
Right, these are the bands. Yep. Very good. Nice.
Cool. Any questions about things so far?
No, I'm good so far.
Cool. All right, then. So as I said, this is both the beginning and the end of the story. So the beginning of the story is that we find the transits. Then we have to kind of go through the process of validating them in many different ways before we, produce the final fit with all of the data and, produce the transit fits shown here. So the very first thing that we did was to turn to a target of opportunity program on Spitzer, which of course, unfortunately, is no longer an option, but at the time, may it orbit in peace. So I had a Spitzer target of opportunity program that had been approved, and this and then so we triggered it to obtain some observations of this system. And we also pursued some ground-based observing opportunities. So if we scroll down to figure 2,
Follow up. Okay.
there we go.
A little too big. One of these days I'll get that to work. Okay.
Yeah, so this shows the ground-based photometry that we also included in the FIT. So the top 2 rows are the Spitzer transits that we obtained through this target of opportunity program. These were actually obtained in kind of like December and January, so some of the very last Spitzer observations that were taken.
Wow.
So the color coding matches from before. We actually, so it turned out Ian Crossfield's Spitzer team had also locked on to this system as interesting for being atmospheric targets for future study with Hubble and the James Webb Space Telescope. And so his team provided this first Spitzer transit of TOI 451d, the 696 labeled one. So in all, we ended up with 5 Spitzer transits, 3 of TOI 451d and 2 of 451c. When we had triggered these observations, we hadn't realized that 451b, the short period small planet, we hadn't realized that it was there, so we didn't know to target it with Spitzer. But as you'll see in this last panel, we just happened to get a transit of it just by chance. So it was an overlapping transit with 451d. And it's maybe not that coincidental. We did ultimately spend quite a bit of time on Spitzer. So these are zoom ins, but we had longer transit baselines. And so 451b is the short period small one, is actually only has a period of 1.9 days. So I've actually not gone through the math, but it may not be all that unlikely that we did actually catch a transit of it. And then lastly, we also got some ground-based observing thanks to the TESS follow-up program. So this is a light curve just catching the egress of the transit from PEST and the ingress of the transit from LCO.
Yep. Bang, bang.
Yeah, and so data like this are particularly useful for follow-up for 2 reasons. The first is that for young stars, like you saw in the previous figure we were on, there's a lot of stellar variability. The star is doing a lot of stuff. There's all these spots. And that signal is mitigated when you move to the infrared. So spots. So when we move to Spitzer, where we get these longer wavelength observations, it allows us to go like, oh, spots are or are not affecting these data.
Right.
And then secondly, TESS has really large pixels. And so often there's multiple things, there could be multiple stars in the aperture at once. Okay. And so Spitzer has much finer spatial resolution. For this particular system, that wasn't critical, but for some of the previous young planets we've looked at, that actually was extremely important.
Definitely. Okay.
Sweet. Okay, so this is the data that we got on the planet itself, but then there was a lot of other data that we collected that went into this whole process of trying to understand the system. And so I think I will maybe, let's take us to figure 4.
Spectrum. Okay.
Yeah.
All righty.
Yeah. So this is data from the literature. This is just an SED of TOI 451. And this is just an example of kind of the information that we collected on this star. So we collect photometry, information from Gaia, and try to understand what this, this overall star and anything else in the system might look like. So here, what you can see is that there's a bit of an excess at the infrared, the far infrared wavelengths on this plot in 2 of the WISE bands, where the star is a little bit brighter than what the model would suggest.
Yep.
And this is suggestive of a cool debris disk. So coming back to what we said before,
Right.
this star does not have one of those beautiful giant disks. It's too old for that. But at 120 million years old, sun-like stars do sometimes have these cool debris disks.
Mhm.
And so this is a similar, this would imply a fairly cool disk at around the same distance as our asteroid belt. But it's not something we've studied in detail at this point.
Okay.
The other thing that we learned is that this star TOI451 has a distant stellar companion. And so if we go back to figure 7, I can talk a little bit more about that stellar companion.
Aha. Okay.
So the astute listener might have seen that there are 2 red stars on this plot.
At the time, but I let it roll.
Yeah. So the second red one at the redder BP minus RP color is TOI451b. So this is a co-moving but very distant, like 5,000 AU stellar companion.
Okay.
That we think is actually composed of 2 M-dwarf stars. So we have TOI451 and its very close planetary system. Right. Those 3 planets, actually I never said it. So the innermost one is 1.9 days, and then 9 and 16 days. Got it. And then we have a debris disk much farther out in the system, and then much farther out we have the binary star, which itself is probably a close binary.
Okay. Right. So it's a triple with planets.
Yeah. Hierarchical triple system with planets.
Very good.
And so TOI451b, oh, that's confusing. TOI451 capital B provided another kind of fun opportunity to bring some more stellar physics into this exoplanets paper. And so if you scroll down to figure 9 in, I guess technically in the appendix, but
no. Figure 9?
Figure 9, yeah.
Appendix yet, so
there it is.
Alex.
Oh yeah, no. So we talk in the appendix. No, it's fine. That's the right figure. We talk in the appendix a little bit more about how we got to this particular plot. So this shows the near ultraviolet excess as a function of spectral type or color. So this is data from Galax, incorporating yet again more public access large surveys. And so ultraviolet excesses are indicative of young stars as well. So similar to, rotation period slows as a star ages, activity declines as a star ages. And so the ultraviolet excess declines as well. For TOI451, the planet host itself, so again, that's the blue early type one. At this age, it doesn't have an excess. We wouldn't expect it to. It just has whatever UV emission is photospheric. But TOI451 capital B, the stellar companion, is elevated above the levels that we would expect for a above the level, TOI451 capital B has elevated levels of UV emission, which is an additional piece of evidence that it is a young star.
Even accounting for the fact that it's a binary.
Yes, yeah, so actually this particular set of axes, so since the binary is, we think basically, it's probably gonna be something like 2 equal mass companions is actually not affected by the star being a binary, coincidentally.
Okay.
Yeah, so this we think is might be particularly interesting for Pisces-Eridanus as a whole, because that is telling us that this publicly available UV data could help us to identify stars in Pisces-Eridanus for especially the low mass members. So the orange points here are the Pisces-Eridanus members.
Right.
The green are the Pleiades. Pisces-Eridanus cuts off around M0, but that's not because there aren't, M dwarf stars in Pisces-Eridanus. We just haven't identified them yet.
Right, because there's Pleiades and Hyades. Okay. And what are the dotted lines?
Oh, the dashed lines show the detection limits for the clusters. So the blue line is the detection limit for the Hyades. And the orange line is the detection limit for Pisces-Eridanus. But that is from, but that doesn't mean that, you can't detect them in the UV, just that you need deeper imaging than what we analyzed.
Right. Very good.
Awesome. So I think with that, I think the last thing that I would mention is that, in order to validate a planet, we have to assess the probability that it's really a planet versus the probability that it's one of these other possible binary systems, things masquerading as planets. A priori, it's fairly unlikely for a multiple planet system to be a false positive. But we did go through those steps anyways, but I'm not going to go through them in detail because yeah, because I think most people don't need to be convinced when you look at the transit light curves. So maybe we can go back up to figure 1 and we can end back where we started, which is with the TESS data.
It's the money shot. Okay. Let's go back.
Yeah, so this is our key figure again. We have the 3 planets here. I never told you the parameters of them, but they're actually very easy to remember. So TY451b, C and D are 2, 3, and 4 Earth radii, respectively, at least if I round. So B is orbital period of 1.9 days. This is the 2 Earth radius planet. C is 9 days, and this is the 3 Earth radius planet. And D is 16 days and is the 4 Earth radius planet. And these planets are, in particular C and D, are very good targets for atmospheric observations. And so I hope that they will help us understand more about what, sub-Neptunes and super Earth's atmospheres look like.
Right. And can we get a handle on 451A on the host star?
Sorry?
Can we get a handle on the mass of the host star?
Oh, yeah, absolutely. I should have talked about that when we looked at the SED. So the host star is fairly similar to the sun, actually, in terms of mass. So it's like 5% less massive than the sun, and it's a little smaller because it is younger.
Right. Very young sun. Okay. Nice. Very nice. So let me ask then. Well, first of all, thank you for going through this really lovely article. Caught my eye when I went through it. Where do we go from here, given what you've published? So I have a couple of questions there. So one, this is Article 4 in the THYME series. Is there going to be an Article 5 and Article 6? And my second question is, you hinted at a little bit, since these would be prime atmosphere characterization targets for these Neptunes and sub-Neptunes and super Earths. So where do we go over the next 5 years with these objects?
Yeah, I think there's a couple of different directions. So first I can answer the question of whether there's THYME 5, which is there is. It came out at a similar time to THYME 4. And this is another system that was led by Ben Toffelmeyer. And this is another really great story that connects stars and planets in a really fundamental way. So I definitely encourage all of our listeners to read that paper. And we do, we are looking at some more young planets from TESS now. So I think we'll keep going. And in terms of the discovery side of things.
So are you gonna do follow up on the characterization of these atmospheres, or keep up the hunt?
So I think I do not personally have goals of pursuing that. It's not a skill set that I have developed so far. My PhD thesis was really in stellar astrophysics. but I'm sure other people will, and I really do look forward to those results. I'm actually already aware of some proposals in to do Rossner-McLaughlin measurements for the planets in the system to try to understand the spin-orbit alignment.
Okay. No, I'm not aware of those, but
there was actually a research note, AAS research note presenting additional TESS observations of TOI 451. So TESS came all the way back around and observed the star again. And that team already published a research note on that because they were preparing for proposal for Rossner-McLaughlin measurements.
got it. Cool.
But yeah, I think I would say generally over the next 5 years, I would expect certainly mass measurements. If this were not a young star, we definitely could get mass measurements of these planets. But there's been a lot of work on how to measure planets in the presence of stellar activity signals. So I hope that we'll be able to measure masses for the planets in the system and try to study their atmospheres both with Hubble and with the James Webb.
Okay. Let me ask a silly question, or at least a naive question. Since I'm good at exposing my naivetes. So how many of these young planetary systems have we found? Or are we talking 10, 100, a million?
We are on the order of a few dozen of them.
Okay.
Yep. And that's from a combination of different surveys. Certainly TESS is playing an important role in that. K2 played an important role of that, as are many of more independent efforts independent of these large surveys.
Great. So maybe over the next 5 years, we'll get to 5 dozen?
Maybe. I think, thinking about the planets from TESS, my research group, I had my group meeting right before this, and they asked this question of how many have we discovered in TESS data versus how many planets are there in TESS? So the answer, I don't fully have an answer of how many young planets we know of, but it's something like 10. And we might expect we might expect somewhat more than that if it was a strict percentage of, if 10% of all the stars are what we would call young, we might say 10% of all the planets are young. We aren't too far off from it's like we're in the right order of magnitude for that. But young planets are hard to find because stellar activity can be problematic. So flares as well as the stellar rotation.
Right, exactly. Very cool. Well, there'll be a lot of fun stuff to look at over the next 5 years or so on these young planets. Elisabeth, I want to thank you so much for walking us through your article and spending some time.
Yeah, my pleasure.
All righty. Thank you, everyone. We'll see you on the next one. Bye-bye.